So, just to kind of go over this briefly, everything on our solar system came from exploded stars, including the water in the ocean. So, exploding stars. So, here you've got this nebula that comes from an exploding star, and they condense into a protostar, and the water on planet Earth is already here. And there's protoplanets around a protostar, already has the water on there. It's not in ocean form yet, but the molecules of H2O are already here. And about 4.5 billion years ago is when the Earth, with all the oceans, were formed. And this word we learned, density stratification. So the most dense materials, you should be able to draw this. Metallic core, and the inner core is solid because the pressure is so intense in the center of the Earth, and the outer core is liquid because it's so hot. Things are melted. This is the rocky mantle made of rock, and then the outer layer, the lithospheric crust, and this is called density stratification. Density meaning dense, and stratification meaning layer. So the Earth is layered according to its density. And the way that the oceans became was due to outgassing. So water used to be, when the Earth was just formed in this protoplanet stage, the water was just kind of everywhere. How did it get to the surface, right? Because water is less dense than iron and rock, so it got through outgassing. So outgassing happened because the volcanoes when the volcano exploded out, water came out as well as all the other stuff that came out of the volcano. So water vapor came out, and it was in clouds, and it rained down onto a very molten baby young Earth, and it boiled back up again and rained down. And then eventually that water collected into the oceans, very quickly after the beginning of the Earth. And here you have 97 or more than 97% of water on planet Earth is in the ocean. So that's why the ocean is so important. And again, scientific method, why do we not just say stuff? You have to first make an observation and have a hypothesis to explain that observation. So we observed that the continents appeared to look like they fit like puzzle pieces, so we had to make a hypothesis. Well, first it was continental drift, but then there was no way to test the observation, so you kind of had to make different observations, and we observed more and more and more evidence until finally we called it plate tectonics because of all this information. And then finally you get enough evidence to come in to really support a much stronger theory. Then we're moving on to the history of oceanography. So you should just be able to remember how we did this in class, like list 3 or 4 or 5 things for each of these groups. So you should be able to list 3 or 4 important things that we learned about the Polynesians, and list 3 or 4 important things that we learned about, especially the Library of Alexandria. So what was there? They knew the Earth was round. They collected a lot of maps and scrolls. It was the first library. They invented longitude and latitude. It was burned to the ground by the Christians. Remember the Polynesians 10,000 years ago? They were sailing really far. They discovered all those islands in the Pacific on their small little boats, and they navigated from the stars and following birds and clouds. Vikings went to North America quite a while before Christopher Columbus, but there was nothing to rape and pillage, so they left. The Chinese, remember, their huge ships, their watertight compartments, rudder for steering. They invented the compass, and they had ships with lots of masts on them, and they also may have been to America before Columbus. There's some evidence for that, but still not maybe as strong as evidence as the Vikings, where you actually still have their settlements. But there is some evidence that the Chinese might have been here. And remember, I had some different cartoons and drawings of some of the early scientific voyages that were just for science. Some of those guys like Magellan, who first went around the world and, started collecting things and sampling. You should be able to understand the longitude and latitude grid. So the latitude are the ones going like this, telling you how far north or south you are, and the longitude going like the segments of an orange, telling you how far east and west you are. And that's important because if you are on the ocean, you need to know where you are so that your ship doesn't crash. And then, we've just the ones, I know the book goes into a lot of these guys, and I'm not going to kind of ask you to memorize stuff and list it on the test. But the ones that we discussed in class are the ones that I think are really the most important. I mean, we definitely talked about Alvin the submarine quite a lot, for example. So again, here's your Library of Alexandria. They kind of had these early maps. They knew the Earth was round. Here's your diagram. Longitude, the orange slices telling you how far east or west you are, and latitude, the parallel lines going from the equator toward the poles to tell you how far north and south you are. And again, the year 300, people already knew all this stuff. And then, after the library was burned down, that knowledge went away. So let's move on to density stratification, and I recommend that you be able to draw this for the exam. And some people are better artists, but draw and label is always the best. So again, here's your density stratification with your core, your mantle, and your crust. But the better view of it is here's your lower mantle that's made of rock, and the upper mantle, which on the test, I want you to be able to remember this word. So remember how in class the other day I was saying stuff like, you don't have to be able to remember the word pterogenous when we're talking about sediment. I'll have the word pterogenous on the test, and then you'll have to kind of answer questions about the word pterogenous. Asthenosphere is not like that. I actually am not going to have the word asthenosphere on the test. So you need not only to remember what the word is, but, as best as you can, how to spell it. So the asthenosphere, here's the spelling. Pause it and write it down if you want to. You should be able to draw this. So the asthenosphere is the upper part of the mantle that's mattress-like or Play-Doh-like or plastic-like. It's capable of flowing. So it's not quite like a liquid or quite like a solid. It's like a soft, squishy, molten solid that moves. And that is that mechanism for plate tectonics. Then above the asthenosphere, there is the rigid, which means it's breakable, rigid, like a piece of like stick. If I cracked it in half, it would be rigid. So the lithosphere or the lithospheric crust is a solid that floats on top of the molten asthenosphere. And then you've got two kinds of lithospheric crust. You've got oceanic crust, which is made of basalt, and then you've got continental crust. And remember, we were lifting those two rocks in class the other day, and the basalt is much, much, much more dense, which explains why when two plates converge, the denser crust subducts underneath the less dense crust. So you should be able to draw this and label it and say, what it is. The asthenosphere is the lower mantle is rock, and asthenosphere is molten, and lithosphere is rigid, and oceanic crust is made of basalt, and continental crust is rigid, but it's less dense than oceanic crust. So, and here's yet a better version of this. So same thing. Here's your basalt. That word also on the test. Basalt crust and continental crust, and your rigid lithosphere up here, and then your asthenosphere. So this, you could draw either of them. This is fine. And then your rocky mantle. Giving you a chance to gaze at it. It's going to be on the test. Remember, and I think by now it's already up there, I have listed the two essay questions that are going to be on there. And one of the essay questions is list and describe 6 pieces of evidence. So here's a list that I made, and there's way more than 6, but listing means listing and describing, not just listing. So let's just go through each one. Visual fit of the continents. You guys should know what that is by now. They look like puzzle pieces, so you could write that and then explain how South America and Africa kind of look like they fit together. The distribution of earthquakes is the thing, but then you'd have to kind of describe, where the earthquakes are and what that means. Let me just say one other thing. On the test, there's a question that asks how scientists know about this density stratification, because of course no one's been down here to see the layers. And remember that whole talk that we gave about the seismologist who studied earthquakes, and that's how they knew it. So that's on the test. So how we know this information, again, is through seismologists who have told us because of the pattern of the earthquakes. Okay. So this one here, deformable asthenosphere under rigid plates. Well, how do we know this? We've already described what that means. You could list that, but you could describe it saying that, seismologists discovered all these layers with this deformable asthenosphere, blah, blah, blah. I have all these, I think, more or less in order. Remember those paleomagnetic stripes? And here I have a piece of paper, so I could actually do this for you. So here would be your Atlantic Ocean, right? And it would be opening up like this. And there would be stripes on the sea floor, whereas this would be the youngest ocean. Here would be like a new Atlantic. And then here would be a medium age Atlantic. And then here would be kind of a teenager Atlantic. And here would be kind of a middle-aged Atlantic. And then here would be the Atlantic that you would see today. But the age would be like that. Okay? Remember polar wander? So that would mean that it appeared that the poles wandered, but really the plates have moved. I might have to sneeze. Okay, remember there were tropical plant fossils at the poles and evidence of glacial striations in the tropics. So the only way to explain that is the continents must have moved. Remember the hot spot evidence. I'll use my piece of paper again. So here's the plate. Here's the hot spot. My pencil is the hot spot. And as the how do you do this? As the plate moves over the hot spot, those island chains are formed, and only the most recent volcano is active. And I think there are some videos of Hawaii being formed, so that are way better than me with a stupid piece of paper and a pencil. So, check that out, and then you can explain that. The age of the sediment as well as the distribution of the sediment. We covered that in the most recent lecture. So you'd expect that the youngest sediment would be nearest the ridges where new seafloor is formed, and the oldest sediment is furthest away from the new seafloor. And again, the thinnest sediment is at the top of the ridges where the new seafloor is, and the thickest sediment is furthest away. Again, the location and shape, these same animals and plants. So this is the plant, this is the animal on opposite sides of the Atlantic, one in Africa. We didn't talk about terrains, so skip that. The pattern of earthquakes at the subduction zone. So remember the the shallow earthquake, the medium earthquake, and the deep earthquake all go in a very specific pattern. And really that explains that, subduction you'd expect to look like this as one plate subducts under the other one, and you do see shallow, medium, deeper earthquakes in that pattern. And then you've got your African rift zone and your Red Sea as modern examples of what an ancient Atlantic Ocean might have looked like. And then you actually, when you go down into the rift zone and look at the photos from Alvin, you see that there are vents that look like lava coming out of the bottom of the sea floor. Also, these patterns of seamounts and guyots look like they spread away from a spreading center. So I think I have some of the cartoons of these. Here. So here's just Pangea breaking up. And here's, again, you've seen this one before, the puzzle piece pattern as well as the different species living on, the same species living on different continents, which no other way to explain. And the glacial striations in the tropics, so evidence of glaciers in tropical areas, and there's also evidence of tropical things in places that are now in the ice. Here's your pattern of earthquake distribution, and you can see how the earthquakes are really right along the edges of the plate. Right along the edge of the plate, earthquakes right along the edges of the plate. So it just kind of, the mountain ranges match up with where the earthquakes are. The mountain ranges match up where the earthquakes are. So that's another piece of evidence that was on that list. Here's your drawing of the striping that I did with the piece of paper. And there's the age of the seafloor, so the youngest seafloor. At the tops of the ridges, at the tops of divergent plate boundaries where new seafloor is formed, you see the youngest seafloor, and you see the oldest seafloor furthest away from the spreading centers, it furthest away from the spreading centers where